Hello, welcome back. So in the last lecture we studied various properties of orthogonal transformations, specifically rotations in 3 dimensions. So by now you must be wondering, is there more? We have studied rotations, we have studied translations. Is there more? I mean, the set of rigid body motions, how should we think about it in general? And here there is a theorem, and the theorem is that any rigid body motion can be expressed as an orthogonal transformation followed by a translation. So we don't need to consider anything other than orthogonal transformations and translations. Among orthogonal transformations, there are ones which have determinant +1 and determinant -1. And we will be concerned with those transformations which have determinant +1. And sometimes these are called proper rigid body motions, and the term special orthogonal group is used. Okay, so now we can ask the question, here is a certain form of this transformation. Can we say more about the structure of the set of rigid body transformations? So one observation here is that the composition of 2 isometries is an isometry. So how do we go about proving this? So there is one isometry given by the formula here, and let's say another isometry given by this formula. So here A1 and A2 are the orthogonal matrices. They will correspond to the rotation part if the determinant is +1. And then there's a translation given by T1 or T2. So if we combine these two, do we get another isometry? Well, that's a fairly straightforward thing. We just do the algebra. So here, let's say we have the point A, we apply psi2, and then we apply psi1. So that will give me this kind of an equation here. And then if I crank through the algebra, I get something else, which is A3A plus T3, where A3 is A1, A2, and the T3 is A1, T2 plus T1. And this is again in the form of an orthogonal matrix multiplying a vector plus a translation. So what we see is that the composition of 2 isometries is therefore an isometry. More generally, isometries constitute a group in the mathematical sense. And again, if you don't know the definition of a group, you can look it up on Wikipedia. So when you have elements of a group and some operation, we can get new elements of the group. And there has to be an identity element. So what will be the identity isometry? It will correspond to A being I. So the orthogonal matrix is I, which does nothing. And the translation part should then be just 0. And that if I have an isometry corresponding to an orthogonal matrix, which is the identity, and a translation which is 0, I will have nothing happen as a result of it. There is an inverse. So if there is a isometry specified by the orthogonal matrix A and translation vector T, we can compute what should be the isometry applied to the result of the first transformation so as to bring us back to the identity. And this I leave as an exercise to you. You should be able to work this out. Isometries are, the composition of isometries is associative, and that's again a straightforward thing to work out. Now let's turn to the same form that transformation is matrix multiplication of the input vector A, and then after that there's an addition of a translation vector T. But now what we do is we generalize a little bit. What we say is that A is no longer required to be orthogonal. A is any non-singular matrix in this case, meaning that we require that its determinant not be 0, but that's it. So you can see clearly that this is a proper generalization of the set of isometries or rigid body motions, because orthogonal matrices are obviously non-singular, so everything works. It's going to work out there. But what does this bias, this notion of affine transformation? It's a more general notion. What does it bias? it buys us more flexibility. So here I'm going to give you an example where this is the input, and just for example, you can think of the 4 points of the square as input. Now there are orthogonal transformations we know about, such as rotation, right? That will give you something like this. But rotations followed by translations cannot give you effects such as an isotropic, scaling, or shear. However, these can be captured by affine transformations. So for example, an isotropic scaling. Let's just think of what that matrix A must be. For example, it could be something like 2, 0, 0, 1. With a matrix like that, what will happen is that the x dimension will get magnified by 2 and the y dimension remains unchanged. So that's an anisotropic scaling, and this is allowed under the set of affine transforms. And we can have other kinds of matrices A, and some of these will give rise to shears. So, and obviously rotations are already included. Okay. Let's test our understanding of affine transforms versus isometries by studying how many parameters are required to specify an isometry versus an affine transform. So let's think about isometries. So isometries in 2 dimensions. So in 2 dimensions, an isometry is a rotation, and how many parameters are required for that? 1. And a translation, for that you require 2. So you need 3 parameters to specify an isometry or a rigid body motion in 2 dimensions. What about for affine transforms? So we're going to have a 2 by 2 matrix, so that has 4 parameters, and then the translation part, which will have 2 parameters, so therefore we get a total of 6 parameters. Okay, now you may want to think through what will happen in 3D. If you want, pause the video now and try to figure it out before I give you the answer. So in 3D, the isometry will consist of an orthogonal matrix followed by translation. So the orthogonal matrix is going to have 3 independent parameters, and the translation will be another 3 parameters for a total of 6. When we consider affine transforms in 3D, what are we going to get? We're going to get a 3 by 3 matrix, and so that 3 by 3 matrix will have 9 parameters, and then there will be a translation which is going to be 3 parameters, so for a total of 12. So we see clearly that affine transforms are more general, they require more parameters to specify. So the big picture can be understood better if we try to ask the question, what remains unchanged under a transformation? So mathematically, the term we use is invariants. What are the invariants under a transformation? So under Euclidean transformations, we design them to be such that they preserve length. So if we have 2 points, the distance between them should be unchanged. That was essentially our definition of isometry. So under Euclidean transformations, lengths are preserved, angles are preserved, as well as area and volume and so forth. Under affine transforms, we already saw, just think of that anisotropic scaling case, that lengths are not preserved, angles are not preserved, areas are not preserved. However, some things are preserved. Remember, these affine transforms are linear transformations followed by a translation. And you can see that if 2 lines were parallel to begin with, then if we apply a transformation, these 2 lines will remain lines, and they might be moved about, they might be further apart, but they will remain parallel. Parallel lines remain parallel. Another nice property is that the property of being the midpoint remains. So suppose I have points A and C, and then there is a point B, which is the midpoint of ABC. And now we transform this by an affine transform. The line will remain a line. The lengths may change, but let's say the point A is transformed to here and the point C is transformed to here, the point B will remain the midpoint. So that is preserved. And again, you can verify all these from the properties that you know. Essentially, the fact that there's a linear transform involved makes all these understandable. Okay, so here's the big picture. We have the set of affine transforms, and within the set of affine transforms, we have in there the set of Euclidean transforms. And specifically, there is one particular point. This is the identity. And this corresponds to A equals I, and the translation part being the zero vector. So the identity is included in Euclidean transforms, and of course the identity is included in affine transforms. But the next question we can ask is, now we've got a more general set of transforms, and these constitute a group as well, but are these as general as we need to be? Okay, let's think. There is a set of transformations that are called projective transformations, but let me first motivate why we need them. We studied perspective projection. That's, after all, our main vision motivation here. Under perspective projection, lines on the ground plane which were parallel, they projected to lines on the image plane that intersected. So parallelism was not a property that was preserved, and affine transforms preserve parallelism. So we now know that perspective projection cannot be modeled by an affine transform. And since we want to play around with perspective projection, we need to consider a more general family of transformations. The answer is provided by this family of transformations called projective transformations. These are even more general than affine transforms, and this includes perspective projection as a special case. What are projective transformations? These are linear transformations. Okay, so far so easy. In fact, you don't need to add a translation part separately. The translation can be folded into the linear transformation. But these use something called homogeneous coordinates. Okay, so now we have another new beast to explain. Homogeneous coordinates, I'm really not going to get into too much detail on this, because this is, after all, a course on computer vision and not a course on mathematics. I encourage you to look it up on Wikipedia. I'll just give you a little taste of what this whole idea is about. Suppose we have a point in three-dimensional space R3. So normally we might model it by some three vector x, y, z. These are the normal Euclidean coordinates. What we do is we add another fourth coordinate. So we have now coordinates x1, x2, x3, x4. But the property is that any two such vectors are regarded as the same vector if they are scalar multiples of each other. So in a certain sense, the degrees of freedom are still 3. So sometimes you can think of this as you can go from x1, x2, x3, x4 by just dividing by the fourth coordinate. Now that doesn't do anything very exciting unless the fourth coordinate is 0, and that corresponds to the so-called point at infinity. In fact, there are many points at infinity. So homogeneous coordinates enable one to represent all the things that we have talked about so far, rotations, translations, and so forth, all by a single matrix. So when we are concerned with three-dimensional space, so in three-dimensional space, the normal points would have 3 coordinates, but homogeneous coordinates would make us get to 4 vectors. And so the matrix that would be involved for a linear transformation would be a 4 by 4 matrix. Actually, it will have only 15 independent parameters because overall, if you multiply all the entries of this matrix by a non-zero scalar, nothing changes because scalar multiples correspond to the same point in projective space. These transformations are used a lot in computer graphics because in computer graphics, when you want to render objects, you want to rotate them, translate them, project them, and all of these can be captured as linear transformations in homogeneous coordinations. So there is support for these kinds of computations available in graphics hardware. I am going to stop my coverage of this topic right here because we may need to know a little bit more about projective transformations, but we'll develop it as necessary. I feel that I don't want the course to become a dry mathematical review. So I'll just summarize the final story here. We are concerned with 3 main families of transformations: projective transformations, affine transformations, and Euclidean transformations. Euclideans are the most specific. These are rigid body transformations and they preserve distances, angles, areas, etc. Affine transforms are the next generalization, and projective is the most general of all. Thank you.